Hello everyone, I'm Shougang Yuan from NC State University, and today I'm going to present our work about analyzing secure memory architecture for GPUs. I will start from the motivation of our work, as we know that the hardware-based trusted execution environment has been integrated onto CPUs. However, in data centers, GPU is also the key component, and the trusted execution environment is still missing for GPUs. In this work, we try to explore the design space of secure GPU memory and review the key performance bottlenecks. Now I will introduce the background of our work. First, I want to introduce the threat model. Conventional CPU trusted execution environment assumes two types of threats. The first one is compromised system software, including the operating system and the hypervisor. And the second one is physical attacks. In physical attacks, it assumes that the attackers have the physical access to the remote server and can perform memory bus snooping or memory scanning. It also assumes that the attackers can modify the memory directly. Second, I want to introduce the architectural support. Usually, there are three major architectural supports for CPU trusted execution environment. The first one is hardware key management, which generates the key for memory encryption and integrated algorithms at the hardware boot time. The second one is attestation, which can guarantee that the information can only be accessed by the attested parties. The third one is the secure memory engine, which encrypts the data and protects the data integrity in off-chip memory. Among these three, the secure memory engine incurs the largest performance overheads. The reason is that secure memory engine must be active all the time, and it affects the critical path of memory read access. The scope of this work mainly covers the physical attacks and secure memory engine for GPUs. Similar to the CPU secure memory engine, we assume the processor chip or the processor package forms the trusted computing base. Now I will introduce the background of memory encryption and integrity. The state-of-art secure memory on CPUs adopts counter-mode encryption and boundary circuitry. With counter-mode encryption, the block address and its corresponding counters are fed into the AES engine to generate the one-time PID, and the memory controller can perform encryption or decryption with one cycle exclusive OR operation between the data and the one-time PID. The benefit of counter-mode encryption is that it can hide the decryption latency by overlapping it with memory read. In counter-mode encryption, counter reuse can break the encryption, and hence the encryption counters need integrated protection to prevent counter replay attacks by the boundary circuitry. Also, the message authentication code is needed to prevent the attackers from modifying the data in the off-chip memory. Alternatively, direct encryption is also used for memory encryption in early designs. The main disadvantage of direct encryption on CPUs is that it exposes the decryption latency to the critical path of memory read access. Moreover, the message authentication code is needed to prevent memory tampering attacks, and the Merkle tree is needed to prevent replay attacks in direct encryption. Overall, in counter-mode encryption, the secure metadata includes encryption counters, the message authentication code, and the boundary circuitry nodes. In direct encryption, the secure metadata includes message authentication code and the Merkle tree nodes. Next, I'm going to introduce some related works. There are two most recent works related to our study. They are Graviton and HIX. In Graviton, it assumes the system software stack is untrusted, including the GPU driver and the operating system, and the key GPU management operations are offloaded from GPU drivers to the GPU command processors. Also, it assumes that the attackers have physical access to the GPU and the PCIe bus is protected with encryption. Alternatively, HIX assumes that the GPU driver is running on the CPU enclaves and also protects the PCIe bus with encryption. However, with these two works, the secure memory engine is missing. In other words, the data in the off-chip GPU memory is plain text, and there is no integrated protection to the off-chip GPU memory. Next, I'm going to introduce the secure GPU memory architecture in our design. As we know that GPU performance is highly bounded by memory bandwidth. Hence, there are two major architecture changes on GPU memory hierarchy. First, it has multiple memory partitions and multiple on-chip memory controllers to support high bandwidth requirements. Second, it adopts sector data cache to reduce the bandwidth consumption. To support GPU secure memory, the secure memory engine is replicated in each memory controller in our design. Next, I'm going to present our in-depth evaluation. We start our investigation from state-of-art counter-mode encryption and bonsai merkle tree. In this slide, the figure on the left side shows the performance implications of secure GPU memory, and we also model several ideal designs to identify the performance bottlenecks. The first bar is the naive design, and the second bar is the secure GPU memory with zero encryption latency and hash latency. From the first two bars, we can see that secure GPU memory can incur high overheads, and zero cycle of cryptographic latencies cannot alleviate the performance. The reason is that GPUs are latency tolerant. The third bar is the secure GPU memory design with unlimited capacity of metadata caches, meaning that there are only code misses. The fourth bar is the secure GPU memory design with ideal metadata caches, meaning that all the metadata cache accesses are hit, and there are no metadata readbacks. From the last two bars, we can see that the main performance bottleneck of secure GPU memory is the memory bandwidth due to the additional memory access to the secure metadata. On the right side, we also report the distribution of different memory requests in GPU DRAM, and we can clearly see that accessing the message authentication code and the encryption counters requires high memory bandwidth. Digging deeper, we found that due to sector data cache and the streaming access pattern on GPUs, there are more than 60% metadata caches are secondary miss. Here, we show one example of streaming access with 4 sectors, and each sector is 32 bytes. The first access will be the primary miss, and the remaining ones will be the secondary miss. The straightforward solution to avoid secondary miss is add the miss status handling registers. We also report the performance implications with different number of miss status handling registers, as shown on the right side of this slide. And we can see that increasing the number of miss status handling registers beyond 32 has a small performance gain. In CPU secure memory, previous work shows that unified metadata caches perform better than the separate ones. Unified metadata cache means that all the 3 types of metadata are stored in a unified cache rather than separate ones. However, our evaluation shows that separated metadata caches are better than unified ones on GPUs. The reason is that streaming access will lead to cache thresholding problem, and the newly fetched metadata block will keep evicting each other in the unified metadata cache. We report the metadata cache miss rate in different designs, and we can see that for unified metadata cache, the miss rate of all the 3 types of metadata increase. Now I will present the impact of AES engine throughput. Up to now, we assume that there are 2 pipelined AES engines in each memory partition. In this slide, we present the results when we reduce the number of AES engines from 2 to 1 in each memory partition. As we can see that the limitation of AES engine throughput can be easily addressed with 1 pipelined AES engine in each memory partition. The reason is that for computation-intensive benchmarks, neither the memory bandwidth nor the AES throughput is the main bottleneck. For memory-intensive benchmarks, the bottleneck is the additional memory traffic due to secure metadata access. Only when the memory bottleneck is addressed, the limitation of AES engine throughput may show up. We also use cacti to estimate the die area requirements of a secure memory engine. Overall, the secure memory hardware will occupy around 25% of L2 cache capacity. To quantify its performance implications, we report the workloads sensitivity to the L2 capacity. For some medium memory-intensive benchmarks, they can be sensitive to the L2 capacity. The reason is that reducing the L2 size leads to higher L2 miss rate. However, for non-memory intensive benchmarks, they have small numbers of memory accesses and will not be affected by L2 size. While for memory intensive benchmarks, they have very high L2 miss rate and may not be affected by the L2 capacity that much either. Overall, reducing the L2 capacity has very limited performance impacts in our study. As mentioned earlier, direct encryption can also be used for memory encryption, and the disadvantage of direct encryption on CPUs is that it exposes the decryption latency to the critical path of the load instruction. However, our evaluation shows that direct encryption actually does not affect GPU performance that much due to the latency-tolerant capability of GPUs. In contrast, counter-mode encryption can incur high overheads for GPUs due to additional secure metadata traffic. Memory encryption can provide confidentiality. However, with a strong threat model assuming that the attackers can perform memory tampering attacks, the memory integrity is also needed. In this slide, we show that the direct encryption with MAC can still perform better than the counter-mode encryption with MAC and bound Merkle tree. However, once Merkle tree is supported, it can incur higher overheads. The reason is that, given the same memory protection range, Merkle tree can be higher than the bound Merkle tree. On one hand, a higher integrity tree implies that the integrity verification process needs to traverse a longer path and potentially incurs more traffic. On the other hand, due to the array of the integrity tree, a higher tree will also lead to more contention in the Merkle tree cache. Based on our evaluation, we found that, first, due to the latency hiding capability of GPUs, direct encryption can be a better choice for GPUs. Second, one pipelined AES engine per memory partition can provide the AES throughput balanced with memory bandwidth. Third, metadata caches can reduce memory traffic, and separate the metadata caches perform better than the unified ones. Fourth, sector data cache and streaming data access on GPUs make the misstatus handling registers necessary. Fifth, to support memory integrity, both counter-mode encryption and direct encryption need to be further optimized to reduce the overheads. Overall, our conclusion is that we need to architect GPU secure memory differently from it on CPUs. Thanks for listening to my presentation. To learn more details about our work, please join the live talk in ISPA's main conference.